So yeah, this is a good example of what I mean when I say you do the PMI proof, but then there's a little bit of extension to perform. Now, we've got use induction to prove that for all positive integers, and we have 1 plus 3 times 1 plus 3 squared times 1 plus 3 to the 4 times 1 plus 3 to the 2n take 1 equals 3 to the 2n, 3 to the 2 to the n, take away 1 on top of 3. Now, for this, this is a product. It's a product proof because we can see each term is multiplying each subsequent term. Okay, so it's a product. Now, whenever I teach PMI, I like to go by the acronym STATE. All right, this is what I like to remember. So we've got state the proposition. We always state the proposition because then when it comes right to the end, all we have to do is refer to P of n. We define P of n, we declare P of n. State, test, assume, prove, explain. That's what state stands for. Now, you don't have to follow this procedure. You do have to have the correct form, but you don't have to write these words out or anything like that. It's just that you have to satisfy, you have to have made a statement of the proposition, you have to have tested the first case, always the first case, that first domino needs to fall over. You need to assume P of k, prove P of k plus 1, and then explain. Okay, so let's state the proposition. This is how we make a statement, and this is going to be our opening line. It's going to be something like P of n is, and then all we have to do is rewrite the top line that's given to us. 1 plus 3 times 1 plus 3 squared times 1 plus 3 to the 4 times 1 plus 3 to the 2 to the n take 1 is equal to 3 to the 2 to the n take 1 on top of 2. P of n is this, but for what? For all n belongs to the set of positive integers.
Why do we say positive integers when you could instead use natural numbers?
That's a good question. What's the difference between a natural number and an integer? That's a good question. I don't think there's a significant difference, not for our purposes. Yeah. I think convention for now. I might look it up. I'll let you know. Good question. Okay, are we happy with this notation? All right. For all n being the variable we're talking about, epsilon belongs to z, the set of integers that are positive. Okay, you can write the words if you want, but much faster to do it like that. So that's step one. That's our proposition, right? We've performed the state. So I might write up state. State. Done. Okay, next we have test. Now we're going to test for the lowest positive integer, which is n is 1. We have to test for the lowest positive integer, which is n is 1. So if we take n is 1 and we put it on the left-hand side. Now, we've got two ways we can grab it, okay? It's that first term there, 1 plus 3, which is going to be 4. Or we can look at this here, where we put the number 1 in, okay? The first member of the series is going to be 1 plus 3 to the 2 to the 1 take 1. Okay, that's going to be 1 take 1 is 0, 2 to the 0 is 1, 3 to the 1 is 3, 1 plus 3 is 4. The left-hand side is 4. Okay? The right-hand side will be 3 to the 2 to the 1, take 1, divided by 2. So 2 to the 1 would be 2, 3 to the 2 would be 9, we'll have 9 take 1 on 2. Now, in terms of bed mass here, we need to perform this operation at the top, right? Okay, it's acting as if it's in brackets. 9 take away 1 is 8, 8 divided by 2 is 4. And so what we have then is we have the left-hand side equals the right-hand side, therefore P of n is true for n equals 1. Okay, the test has demonstrated that it's true in the first circumstance. The first domino has fallen, doesn't mean anything. We need to demonstrate that it works for the rest of the cases. Okay, state, test, assume. Okay, and so here we're pretty much making the same statement except in terms of K. Assume P of K, the proposition with regards to K, which is this whole thing but with K instead. So 1 plus 3. There's a lot of repetition involved in these, isn't there? 1 plus 3 to the 2, 1 plus 3 to the 4, 1 plus 3 to the 2 to the K, take 1. That's definitely going there. Is equal to 3 to the 2 to the K, take 1, divided by 2. So let's assume P of K is true. Assume P of K is true for all K is a positive integer. Alright, so you can see state, test, assume. So we've got state, isn't it? State, test, assume, prove and explain. Now I'll spin the board around in a sec. Or are people happy for me to clear some space? Yep, everyone's up to date. I might just spin it around so I can refer to it. And in future I'll get 2 boards in, I'll try to get 2 in. How long is this going to be?
I can see if you had a maths teacher who annihilates whiteboard using physics and strength.
Okay. Let's go for the proof. So we've done state, test, assume, prove. Okay, so to prove it, we need to consider P of K plus 1. And so again, we're restating the proposition, which is P of K plus 1. So for P of K plus 1, we're going to have 1 plus 3 times 1 plus 3 squared times 1 plus 3 to the 4 times 1 plus 3 to the K times, it's K, 2 to the K, take 1, times 1 plus 3 to the 2 to the K plus 1, take 1. Okay, that's the P of K proposition. Here's the P of K plus 1, isn't it? It's the next term in the sequence. It's one more further along than the K term. Okay, and we have 1 take 1. You can collect them at any stage. You can simplify that to just P of K. Now, if it's true, if P of K plus 1 is true, here's what it's going to equal. It's going to be 3 to the 2 to the K plus 1, take away 1 on top of 2. That's what we need to prove. Okay, so we've stated what P of K plus 1 is. Now we use our assumption. Remember, we assumed P of K is true, and this whole thing here is P of K. We assumed that that component is true, so we can substitute in the P of K that we've stated before, which is 3 to the 2 to the K, take 1 on top of 2. Okay, on the right-hand side of the P of K proposition, we've got this one. Is everyone happy with that? Yep, because because I'm using the board up here, we can't see the other side. 3 to the 2 to the K, take 1. Excellent. So that's that part there, but we've still got that last term remaining, the P of K plus 1 term. So that's going here, isn't it? 3 to the 2 to the K. I'll simplify it in this step. Now we're trying to demonstrate that this and this will collect to that. Okay, we need to collect them together somehow. So all we need to do is multiply them. Now, can anyone see a quick way to perform that expansion? All right, on I'm just going to write this one. I'm just going to swap those around the other way, the terms around. And then maybe just 3 to the 2 to the k plus 1. Yeah, who said it? Well done. Difference of two squares, right? A take b multiplied by a plus b. Alright, so it's an expansion that pops up all the time in STEM. Always look for it. A squared take b squared. So what the two brackets are going to expand to then, let's just leave this half out front for now so we don't have to have the whole thing at the top. See, there's 2 at the bottom. I'm just pulling that out the front. And if we have a take b multiplied by a plus b, it becomes 3 to the 2 to the k multiplied by 3 to the 2 to the k, alright, a squared, and then take away b squared. So take away 1 squared. So the first term squared, take away b squared. Okay, now we're almost there. 3 to the 2 to the k times 3 to the 2 to the k. There's a number of ways to think about this. I reckon this is going to be the best way. They have the same base, right? They have the same base, which means you can add the powers together. So what it would collect to is it's 3 and it's 2 to the k plus 2 to the k. They have the same base, right? So you can add the powers together. That's a direct application of this index law. A to the m times a to the n, a to the m plus n. Same base, so we can add the powers. It just so happens that the powers are the same. Now, 2 to the k plus 2 to the k, another way we could write that is that we've got 2 lots of 2 to the k. Right? If I have 2 to the k plus 2 to the k, right? Or if I have x plus x, I would have 2 lots of x. Here I've got 2 to the k plus 2 to the k. I've got 2 lots, 2 times 2 to the k. Take one, almost there. And then here, 2 times 2 to the k. They have the same base, don't they? The base is 2. And the power on this 2 is 1. 2 to the 1 times 2 to the k. So we can add those together, 2 to the k plus 1. Take 1. Which is what we have over here, isn't it? Okay, QED. And so then we need the last step, which is to explain. And we always write, if you've stated P of n, as I've told you to, this line is always the same. Because P of n, P of n is true. What's the correct way to say? Because P of k plus 1 is true, like this. Because P of k plus 1, P of k plus 1 is true, if P of k is true, therefore P of n is true for all n is z plus. Okay, that proposition always the same. The only thing that might vary is depending on whether we're doing all positive integers. Sometimes we do integers greater than 2, greater than or equal to 2, but it tends to be pretty well that one all the time. So, what does it mean as well? Like, what's the theory behind it? So we tested that first domino, right? Let's say there's a series here, and we're saying, does it work for all of them? Okay, that's what we're trying to say. So here is n is 1, here is n is k, the k term, here's the k plus 1 domino, and then here's the last one, the nth domino. So sorry, the first domino. And so what we've done, here's the theory behind PMI. We've tested the first case, and we've seen that the first domino has fallen over. Okay, the first domino has fallen over. And then we say, all right, let's select some domino in the middle. Let's call that the kth one, and let's assume that domino falls over. Okay, let's assume that one's going to tip over. Let's test. If this one tips over, will this one tip over? And what we've demonstrated is, if P of k is true, k plus 1 is true. And so what that means, we've demonstrated 1 is true, so that means 2 has to be true. Because if k is true, k plus 1 is true. So it means subsequent dominoes will always fold over. So if 1 folds over, 2 folds over. And if 2 folds over, 3 folds over. And it works for every positive integer. So it's just beautiful. It's just beautiful, beautiful proof. The whiteboard's very ugly though. We've got to sort that out. Okay, all right, so that's part A. Max, you've got a question?
Do you include P of 1 in the explanation?
Because P of k plus 1 is true, P of k is true, yes, we do. Yeah,
P of 1 first.
Yeah. Because P of 1 is true, and good point, thank you. Because P of 1 is true, and P of k plus 1 is true if P of k is true. Good pick up. Yep. All right, so let's move on to the next part then, which is part B. Hence, simplify this expression, stating your answer as a single fraction. Now I'm going to use this side of the board because it's much more cleaner. You'll break the recess in a sec. Okay. So we're told evaluate 1 plus 3 to the 4 times 1 plus 3 to the 8 times 1 plus 3 to the 64. Okay, that's what it wants us to evaluate and to simplify. Now remember, we've proved that 1 plus 3 times 1 plus 3 squared times 1 plus 3 to the 4 times 1 plus 3 to the 2 to the n, take 1, equals 3 to the 2 to the n, take 1. We proved this is true. Now it's saying, now that we know what this evaluates to, use it to simplify this. Okay, so we have to go, all right, well that means the last term, 64, that power of 64, has to correspond with this number here. All right, the last term is the power of 64, that has to correspond with this number here. So the nth term then is going to be 2 to the n take 1 is equal to 64. All right, in order to solve for n, we need to make them have the same base. All right, so 2 to the power of 2 is 4, to the 3 is 8. Let's write them down. 2 to the 3 is 8, 2 to the 4, 16, 2 to the 5, 32, 2 to the 6, 64. Am I missing one? Hello, James, speaking. Good, thank you. Yeah, absolutely. Yeah, for sure. Jeff? So what do we have? We have 2 to the 6 is 64. So that means n take 1, this power here has to equal 6. If we have n take 1 is 6, n has to be 7.
It's just automatic.
Alright, so let's go through that part again.
Yeah, I'm going to come down to the offer the process to get some new forms placed a little bit. Right, so see it.
And collect the textbook too. We have, this is where it starts. 1 plus 3 to the 4, 1 plus 3 to the 8. The last term is to the power of 64. So that means our power here for the last term has to be 64. So I write that equation out. 2 to the n take 1 equals 64. I must express, let's add in another step. I must express 64 as a power of 2. 64 to the power of 2 is 2 to the power of 6. They have the same base, which means the powers are equal. We have n take 1 is 6, plus 1 to both sides, n has to be 7. Okay, so that means the value of n that is going to provide us with this product series is 7. Okay. Now let's just put that in for now. We have 3 to the 2 to the 7. Take away 1 on top of 2. So it might look like that's the answer, right? It might look like that's the answer, but there's a little bit of difference between these two. And it's this one we're asked to solve doesn't have these beginning two terms. So if we're going to make this one equal to this one, okay, so what we've got here, this is equal to 3 to the 2 to the 7. We established the power has to be 7. Take away 1 on top of 2. If we're going to make this equal to this, then we need to divide this side by that one. Okay, we need to if we're making this proposition equal to this proposition, we need to get rid of that one from here by moving it over to there. So we have 3 to the n, take 1 on top of 2, and that's all going to be divided by this one. 1 plus 3 times 1 plus 3 squared. So that last part's a little bit tricky, but okay, Jeff, Steph, yeah, makes sense. Haley, yep, excellent. And so it says expressing your answer as a single fraction. So at the moment we've got it as sort of this complex mess, but we can simplify this term at the bottom, right? 1 plus 3, that's 4. 1 plus 3 squared will be 10. 10 times 4 is 40. So we'll just tidy that up. 3 to the 2 to the 7, take 1. On 2, on 40. 40 by itself is on top of 1. And whenever we're dividing fractions, A times D on top of B times C. So this will become 3 to the 2 to the 7 on top of 8. Alright. Feeling alright? Yeah. So look, have a breather. We'll come back, we'll maybe chat a little bit more about that one in particular, but and see how everyone's feeling. If you boys can just grab your textbooks and yeah, enjoy your recess, guys. Matt.